Thank you very much. And first of all, let me thank the organizers for organizing this event. I really look forward to this week, and it's great to be back in Lumini. So I will be speaking about certain higher structure that appears when you study fibrations with certain duality properties, namely oriented fibrations that have Poincaré duality fiber. This certain higher structure governed by Kontsevich Lie graph complex that you can define. And basically the main takeaway is that this, what I'll try to convey is that this actually allows us to connect problems in classical problems in commutative ring theory about multiplicative structures on minimal free resolutions, and also problems in differential topology, such as the problem of putting smooth structures on a given fibration. This is, I think, very much on the theme of the conference of sort of higher structures in both algebra, geometry, and topology. So let me first say what I mean by graph complexes today. So let me indicate what graph complex I will be considering. So this is the Kontsevich Lie graph complex, or rather the hairy version of the graph complex. And so what is this thing? So it's a certain finite chain complex, and I will be working today over the rational numbers exclusively. So all cohomology, etc., will be with rational coefficients. So this is a finite chain complex, and it's spanned by connected graphs. And I'm not giving a formal definition here. I will just try to indicate what type of object this is, and then we'll move on. So connected graphs with, let me just explain what the parameters here are. So n here is for the rank, so the first Betti number of the graph. And then the L here is, I have L hairs or legs. So these are not, this is sort of, legs labeled by the integers 1 up to L. And then you have internal vertices that are at least trivalent. So the internal vertices are at least trivalent, and then the way I grade this is the homological degree will be the deviation from trivalence. So trivalent vertices have degree 0, 4-valent vertices have degree 1, etc. So okay. And then there's a bunch of, you have to specify signs in the differentials and such, you have orientation data. And this depends on M. So M here is just a parity, it's even or odd. And I will not spell out all of the orientation data. Ask me later if you want to know the details. But this depends on the parity of M, and you have certain sort of what do you usually call it, a ribbon structure. So you have cyclic orders of the half edges adjacent to each vertex. But again, I will ignore sort of giving the full details here. This is just an indication, and then you mod out by this is modulo certain shuffle relations. And again, I will not spell out formally what I mean. I will just try to indicate in an example now what kind of things we're looking at. and then the differential delta is given by edge expansions. Okay, so let me just give an example to show what kind of things come here. So this is This represents an element in, with rank 1. And I have 2 legs labeled by 1 and 2, so this is an element here. Here I have 4 valent vertex, so that deviation from trivalence is 1, so the homological degree is 1. Okay, and if I apply the differential here, I'm going to run through all the the trivalent vertices and explode them to decrease the deviation from trivalence. And the way this works in this example would be, I can explode it in 2 ways, and with certain signs that I will also not explain in detail right now. So you get these types of expressions. And this is the differential going from here to degree 0 here. Okay, so this is the kind of graph complex I'm interested in. And to be like a little bit more formal, if you happen to sort of know this formalism of modular operads and Feynman transforms, so this GM is, if you collect these chain complexes for all n and L, this is a modular operad, well, a twisted modular operad if M is odd. And this is the so-called Feynman transform of the Lie operad. And that's why it's called the Lie graph complex. Okay, that's all I wanted to say about this graph complex, about the definition of this graph complex. But there's the main important theorem which is due to yeah, L, M. So it's a certain parameter that you carry with you. It will be later it will be the dimension of the fiber, but for this definition it only depends on the parity. So you have an even version, you have an odd version. That's all. Okay? It doesn't affect the gradings the way I set it up here. And then you have this. I can squeeze it in here. So the sort of original theorem about this graph complex, which is due to Kontsevich in the vacuum case when L is 0, and then this was extended to the hairy case by Conant, Kasabov, and Vogtman. And then the odd dimensional case was done by Lazarev and Voronov. It shows that the homology of this graph complex computes the rational homology of certain automorphism groups of free groups. So out Fn, so Fn is the free group on n generators, and then here this subscript I will explain in a second. And with twisted coefficients in, well, the determinant representation if M is odd, and the trivial representation if M is even. Okay, and so here if L is 0, then this automorphism group is the outer automorphism group of a free group. And for L greater than 0, this is the semi-direct product of the automorphism group of the free group acting on Fn to the power L minus 1, where out Fn acts diagonally here. And so this gives you an interpretation of the graph homology in terms of sort of classical objects in geometric group theory. And I should say that the homology here is non-trivial in general, but it's largely unknown. So it's a sort of big open problem to actually compute these homology groups. Okay, so that's the graph complex I'm interested in. And the theorem I want to discuss today is that there's another appearance of this graph complex in the context of high-dimensional manifold theory. So the main theorem, let's call it theorem 1, is the following. So suppose I have P pi here is an oriented fibration. With fiber simply connected Poincaré duality complex M of dimension m. So for instance, if you have a closed oriented simply connected manifold, this is, that will give you an example. So let's call these things Poincaré duality fibrations, okay? So for instance, if you have a smooth manifold bundle, these are Poincaré duality fibrations. So if I have such a thing, and if I have a graph homology class, so gamma in HK of this graph complex, then to these two objects I can associate, so then there is a map of degree m times n minus 1 minus k, which is kind of you can think of as a generalization of fiber integration from the cohomology of E, and as always in this talk it will be rational cohomology, to the lth tensor power that down to the cohomology of B. And again, a few coefficients. With certain properties. So first of all, it does extend ordinary fiber integration. So it's ordinary in the sense that if I take a specific class that I'll call epsilon L, and I do this map to a sequence of L cohomology classes in E, this is just the same as taking ordinary integration along the fiber of the product of these classes, taking the cup product in the cohomology of E. So for all, this is for all C1, CL, and the cohomology of E.
So are we assuming smoothness?
No, and this is this will be, this will come later. I mean, integration along the fiber is defined whenever you have Poincaré duality fiber. That's maybe your question. I mean, so you can define this in terms of the Search spectral sequence, for instance. If you happen to have smoothness, you can define it as actual integration, but this is actually not actual integration. But yes. Yes, I was just about to say it, so, but I was interrupted. That's okay. Yeah, so you have this where EL is a specific generator for, so it's this graph. It's this you take the tree, 1, 2, L, and this is a generator for H0 of the graph complex where you have rank 0 and L legs. So this particular graph class, recovers fiber integration for you. Okay, but then the point is you get much more. So in fact, this representation, if you like, of graph homology is faithful in the sense that if you have a non-zero graph homology class, then this fiber integration map is non-zero for at least some choice of Poincaré duality fibration. Pi. So you can always sort of detect graph classes by studying this map for suitable choices of Poincaré duality fibrations. And actually, since you asked about smoothness, it's an open problem to determine whether or not one can detect graph classes by using only smooth bundles. And there are indications as to saying that that might not be the case. So this sort of picks up perhaps some difference between fibrations and smooth bundles. So we'll get to that later in the talk. Okay, so that's the main theorem. So I will now sort of discuss how I prove this. And there are different ways that you might go about trying to prove such a thing. And so I'm going to tell you about the way I prove it. And one of the nice features of my proof, which is maybe sort of a bit idiosyncratic, but one nice feature is that it opens these connections to problems in commutative algebra. So I'm going to approach this using rational homotopy theory and commutative differential graded algebras, models for spaces, etc. So so let's now switch to algebra and define a corresponding notion there. So now my base will be some augmented commutative differential graded algebra over Q. And I think I will start writing K. So to be safe, K is always Q if I happen to write K instead of Q. So the definition is that commutative differential graded algebra morphism from R to S is Poincaré duality morphism if, and then, I mean, you sort of want to model the situation above, if the fiber, which algebraically can be expressed as follows, I mean, the cohomology of the fiber is a Poincaré duality algebra. That is to say, it's, I mean, it is an algebra because we're working with in the land of commutative DG algebras, and then it makes sense to ask for this algebra to satisfy Poincaré duality. Right. And some of the main examples of Poincaré duality morphisms, I mean, we already have one, but it's actually interesting to look at special cases. The first example is if you take the unit map of differential forms on a Poincaré duality space. And here again, I'm not assuming M is smooth, so let's take Sullivan's polynomial differential forms with Q coefficients. That's what I mean when I write omega star here. This is an example of, so M is a Poincaré duality space. This is an example of a Poincaré duality morphism, and the H here in this case is, of course, just the cohomology, which satisfies Poincaré duality basically by definition of Poincaré duality space. And then a slightly different example comes from algebra. So if you have R mapping to R mod I, so R is now just an ordinary commutative graded, graded commutative Noetherian K algebra, and I is a Gorenstein ideal. Then this is an example of a Poincaré duality morphism. The cohomology of the fiber in this case will be the Tor algebra. And the fact that actually by a theorem of Avramov and Golod, you can take, like I is a Gorenstein ideal, actually if and only if this morphism is a Poincaré duality morphism. You can use that as a definition of Gorenstein ideal. And there are plenty of such ideals. I mean, this is something people in commutative algebra study a lot. Okay, and then the third example is, well, the sort of, the one we have up there. So if you have a Poincaré duality fibration, if you look at the induced map on differential forms, so now where this is a Poincaré duality fibration. Yes, so those are some examples. And I guess to be safe, for simplicity today, I'm going to assume that the spaces I consider are simply connected. that's not absolutely necessary, but it would complicate the exposition if I don't assume that. So let's just assume that for today. Let's see. And so now, if you have this type of Poincaré duality morphism, what can you do with it? So that's the first sort of theorem here. So if R to S is a Poincaré duality morphism, then you can find a minimal or semi-free resolution. I mean, S is in particular, a differential graded module over R via this map. And so it makes sense to look at covariant resolutions of S in the world of differential graded modules over R. And R is augmented, so it makes sense to talk about minimal resolutions. So you can find such a resolution that admits a certain higher algebraic structure. Oh, this is S. So that admits what I call a Poincaré duality C infinity algebra structure. So I'll explain what this means in a second. So yes, so I mean, even in this case, I mean, where you look at the ordinary commutative rings, I mean, this is sort of a classical problem. So you can always find a minimal resolution of a cyclic module over the ring, and then you might ask whether there is a multiplication that on that minimal resolution. And this says that you can always find a multiplication of this particular type. So let me explain what these terms mean. I.e., so Poincaré duality C infinity algebra structure means that you have, first of all, a C infinity structure, an R linear C infinity structure. So we have structure maps mu n from nth tensor power of A over R, like so. So this is a C infinity algebra structure over R. So a C infinity algebra structure, or some people call it commutative A infinity algebra structure. So it's a coherently homotopy associative multiplication. And C infinity means that you assume that the multiplication mu2 is actually commutative, and then there are constraints on the higher mu n's, they vanish on shuffles, etc. That's a sort of, so that's what C infinity algebra is. So that's the first part of the structure you have, and then I need to raise this a little bit. So, and you also have a non-degenerate R linear pairing. And this is the degree shift. So this means that the map is of homological degree n minus 2, and then here I have a map, an R linear map of homological degree m. And this is supposed to be a non-degenerate symmetric R bilinear pairing. And such that these two structures are compatible in the sense that if you look at the following operation, so mu n plus 1 hat, so this is an operation that takes n plus 1 arguments from A, and it spits out an element of R. So namely, you pair A0 with mu n applied to A1 up to AN. Now this is an operation with n plus 1 arguments, and this is supposed to be, this operation is invariant up to sine under cyclic permutations. Of the inputs. So this, I mean, this kind of thing has different names. Many people call this cyclic C-infinity algebras or Frobenius C-infinity algebras. I prefer Poincaré duality because it connects to the geometry. Right. So we have this kind of structure, and then minimal. So minimal. I mean, I think I maybe said it, but let me. So means that so A is a differentially graded R module, and it's minimal. That means that when you look at its R indecomposables, this has trivial differential. Okay. So now, as a remark, this is an extension of two classical theorems. You can view this as a parameterized version of Kadaishvili's sort of minimality theorem, but with enhanced by Poincaré duality. So so this generalizes two classical results. First of all, so this is due to Kadaishvili without the Poincaré duality, and then an observation of Stashev, which was reformulated in terms of cyclic C-infinity algebras by Lazarev. So this is in the special case 1. So this is in the sort of case of a trivial fibration. So for M a Poincaré duality space, so it says that A in this case will just be the cohomology of M admits minimal Poincaré duality C-infinity algebra structure. And a C-infinity quasi-isomorphism from the cohomology to the drawn form. So this is the classical result that says that the rational homotopy type of any space, simply connected space M, is recorded by a C-infinity algebra structure on the cohomology. And the observation of Stashev and Lazarev is that if M is a Poincaré duality space, then the C-infinity algebra structure can be made into a Poincaré duality C-infinity algebra structure in this sense. Okay, so that's a special case of this. This is sort of, but this also specializes in another way. So maybe I'll move over here to explain that. So another classical result from commutative ring theory, which is due to Buchsbaum and Eisenbud, is the following. So this is in the case when you look at the second case. So when I is a Gorenstein ideal, and R is just an ordinary graded commutative Noetherian ring without any differential. So so this says that the minimal R-free resolution A of R mod I admits a commutative and homotopy associative Poincaré duality algebra structure. Okay? So R here is R is ordinary. So this theorem specializes to a generalization of this result, namely that they only show that it's a homotopy associative. So, but this theorem is saying that there's it's coherently homotopy associative. So you can view this result as a sort of a supremum of these two observations, if you like.
Was the definition of comp not the definition?
No, it's just you have a mu2 which is commutative on the nose, and which is homotopy associative without any coherent homotopies.
Just mu2 as the symmetry.
Yeah.
You know the high
Yeah,
guy.
yeah, exactly. So it's sort of naively homotopy associative.
Can you say some few words about the proof of this theorem? Or?
Yes, but I don't have time. The proof is not by using homotopy transfer theorem, so that's maybe might interest you. So it uses I mean, techniques from rational homotopy theory about derivation Lie algebra models for spaces and fibrations. So it's a kind of a different type of proof than what you might be used to in this for proving these kinds of theorems. I'm happy to tell you more later. Okay, so then granted the existence of these types of resolutions, we can do the following. So now we can go on and say, okay, so now that we have such resolutions, we can say that, well, okay, so now let's give ourselves a Poincaré, let's call it pi, a Poincaré duality morphism. And then let's give ourselves, so every graph homology class gives rise to a map of the same degree as before. In the derived category. So I'll just, by abuse of notation, I'll just use the same notation. So this will be from the S L-fold derived tensor product over R, going back to R. Okay, so this is a map in the derived category of DGR modules. Okay, so that's the theorem. So now this is a purely algebraic theorem, but it specializes to the theorem in the beginning. By specializing to this Poincaré duality morphism, and then take homology. So to get the map in the first theorem. Okay. So this is in fact a better theorem because it gives you a map in the derived category, not just on the level of homology. And how? Let me just indicate the proof. So let's see. Where do I want to go? Okay, so the proof is basically you pick a Poincaré duality C infinity algebra resolution of S over R, and then you get a chain map by borrowing Kontsevich's idea of these, he calls them partition functions. So you get a chain map from the graph complex like this by Concievich's partition functions. So Concevic used these things to define co-cycles on graph complexes associated to cyclic A-infinity algebras. But that was sort of in an unparameterized setting. So we're now just extending that to the differential, working with differential graded algebras rather than just ordinary fields or rings. And I'll just explain the idea in examples. So the idea is that basically it's determined by, I mean, if you know, it's basically recording the structure of a cyclic C infinity algebra here. So to the corollas, so for the graphs like this, okay, so now I have a three-array operation. I need to get the three-array operation on A, and what I can do is, for the corollas, I just send them to I just use the structure maps of the C infinity structure. Let's see them back here. I hope they're still here. Yes. Yeah, so I use these operations, right? So, and then when you have more complicated graphs, let me just do one simple example to get the idea. So if we take this graph with one loop, so this is supposed to give me a two-array operation. So if I have two elements of A, I send this to, well, I use mu4 hat because I have a 4-valent vertex. And then I plug in A and B in the slots 1 and 2, and then I have this edge here. So what I do is I plug in the co-evaluation, as it were, of this inner product space over R. So I do take the sum over EI and EI dual, where EI is an R-linear basis for A, and this EI, and this is the dual basis. So, I mean, we have this inner product, and we can define a dual basis using this inner product in the usual way. Okay? And then you can imagine doing graphs with several vertices. I mean, you write down similar expressions and just multiply the contributions for each vertex, and then every time you see an edge, you plug in this co-evaluation, so you will have lots of indices running. But there's a general formula that sort of, I hope you get the idea. And this actually defines a chain map here. And then we're basically done, because then, so in particular, so if gamma is a co-cycle, is a cycle, then we get, I mean, we can just restrict to that co-cycle here, so we get this induced map. So we get a tensor like so, and this represents this map that I claimed to exist. Right, and I mean A is a cofragment resolution, so this does represent a map in the derived category. So that's an indication of how the proof goes. And there are some observations to be made here. So the first observation is that this map in the derived category does not depend on the choice of resolution. Okay. Well, you need a C infinity Poincaré duality C infinity algebra resolution, but you can imagine having different such resolutions, and the result will not depend on which one you picked. Okay. So but then you observe that if A can be chosen to be strictly associative, i.e. all the mu n's are 0 for n greater than or equal to 3. That means that we have a strictly associative and commutative Poincaré duality algebra over R. And then if you think about the definition of this map, the trivalent things, I mean, they use mu2, but nothing higher. Whereas the four-valent things are higher, they use, mu3 and higher. So if you have a Poincaré duality C-infinite algebra where these are all 0, then anything you try to build out of positive degree graph homology graph classes will automatically be 0 already on the code chain level. So in particular, this map will be 0 for all gamma with positive homological degree. So remember that the degree was deviation from trivalence. And so the conclusion then of these two observations is that it gives you sort of a meaning to this map. What does this map and the homology clauses constructed using it, what do they do? Well, they obstruct the existence of strictly associative Poincaré duality resolutions. So if you have a non-zero operation, this obstructs this existence of strictly associative Poincaré duality algebra resolutions A. And also minimal or not. So, and this is something that now connects to classical problems in commutative ring theory. So there one is often concerned with finding multiplicative structures on the minimal resolution. You can always find multiplicative structures on some resolution that's typically non-minimal. But now we're looking at a different type of resolutions. We're looking for Poincaré duality algebra resolutions. And because these clauses are non-zero, it shows that you cannot not always do this. And so an interpretation of these operations is that they obstruct that kind of thing. So let me elaborate on this point. And where do I do that? Yes, so, no, sorry. I can't do two at once, no? No. Okay.
Please don't break them.
Sorry. Yeah, that would be a shame. Okay. So returning to these questions, so now if I have a fixed Poincaré duality morphism, you can ask the following question. So let me now just say what I just did. So the basic problem that you might ask is, does S admit an associative minimal Poincaré duality resolution over R? So this is a question, and we can answer. I mean, there are answers to this. I mean, so in special cases, this is a question that has been studied. So here are some answers. So in the case when you look at the sort of trivial fibration, you can, this is precisely the question of whether M is formal or not. So this is yes, the answer to this question is yes, if and only if M is formal over K, in the sense of rational homotopy theory. And so in particular, the answer is no in general. Because there are examples of non-formal manifolds. And the obstructions, we all know that obstructions to formality are given by, for instance, Massey operations, etc. So this is a classical thing to study, right? And this problem specializes to that classical problem. It also specializes to this, again, I already said it, but I mean, in this case, the answer in this case, well, this was actually conjectured by Buchsbaum and Eisenberg. They conjectured that the answer was always yes. So they conjectured but that conjecture turned out to be false. But it's true in some cases. So it's true for when the ideal is a complete intersection. You can use the Koszul complex to write down a Poincaré duality resolution. Or when the grade of I is less than or equal to 4, so the grade is the length of the longest regular sequence in I. And this was observed by Kustin and Miller back in the day. This is like 80s or so. But then it was proved to be false, actually, in general. So false if when the grade is you can find counterexamples in every grade 5 and above, and this was due to Avramov and then Srinivasan, well, not together, but she also studied this problem. So here also the answer is no in general. So the problem that we're looking at is sort of a variation of these classical problems, in that we do no longer require minimality, but we want. So let me just do it like this, quicker. We require Poincaré duality. So here's a question prime. So does S admit an associative Poincaré duality resolution A, which, I mean, minimal or not? So this is an easier problem. If the minimal resolution has such a structure, then of course the answer to this question is also yes, but it could be that the minimal resolution does not admit such a structure, but you can find some other resolution. And this is exactly the kind of thing that in the absolute case, and then for the trivial fibration, this is exactly what this well-known result of Lambrechts and Stanley. So in this case, the answer is always yes. And this is basically this theorem of Lambrechts and Stanley that says that anytime you have a Poincaré duality space, you can find a strictly associative Poincaré duality differential graded algebra model for the Ram chains. Of course, if the manifold is formal, you can take the homology. But if it's not formal, you can still do it, but you will get some Poincaré duality algebra that has a differential, so it's not minimal. So you can always do it for the trivial fibration. So now in this commutative algebra world, this I think is a new problem. I haven't seen this addressed in the commutative algebra literature. So as far as I know, this is a new problem, and I think it's an open problem. I don't know the answer. I think it would be interesting to address.
Do you always assume that everything is simply connected?
Sure. All of the questions I talk about here are very non-trivial and have serious content if in the simply connected case. But it's not really a necessary assumption, but it will be too technical to go into the non-simply connected case. So I don't do that today. Okay. So are you worried about, like, if I would take ordinary, like, commutative rings, they're in degree 0, so they're like not representing simply connected things. Well, you can always, if you have commutative rings, for instance, you take a polynomial ring, a modulo some Gorenstein ideal, well, you can grade that by assigning positive even degrees to the generators of the polynomial ring, and these questions make sense, and sort of, yeah, it's just about regrading the classical situation.
For the manifold case, the Lambert-Stanley result
Yes?
is only for simply connected, right?
Yeah, sorry, okay, sorry, yes, sorry, yes, but that result is for simply connected, yes.
And you object to the always. Sorry? You object to the always.
Yeah, okay, sorry, yes, yes, yeah, no, good point. So, yes, yes, I stand corrected, yes. Okay, right. No, wait, sorry, no, I don't. No, I did state in the sorry, the theorem says I only state the theorem for simply connected fibers, but the other spaces that I was talking about the other spaces, the E and the B. So I actually don't stand corrected. Okay, good. Let's move on. So in this case, a new result, which is a consequence of what I just told you, is that in this general situation, the answer is actually no. So this is a corollary of what we just discussed. Because these graph classes are non-zero in general. So the Lambert-Stanley theorem fails for general fibrations. So that's, I think, is a kind of an interesting outcome. How much time do I have left now?
Legally, yeah, 7 minutes.
7 minutes, okay. So then the last thing I want to discuss, we want to return to this question of smoothness. So I want to say a few words about how these classes might know something about whether or not the fibration admits a smooth structure or not. So let's see. Okay. As you can tell, we don't have these kind of things at my university. So this comes to something that, yeah, so this is a sort of, which, I mean, this comes to the origin of these classes, actually. So we discovered this kind of structure when we studied homologies of various types of automorphism groups of manifolds. So I'll try to give you a sketch of what goes on here. So if we now specialize to smooth bundles, and I will also allow these generalizations of bundles called block bundles. I will not have time to explain exactly what they are in case you haven't seen them. So, but you can think smooth bundles here. So, and gamma is a graph class. And to any such data, and then I can give myself a sequence of characteristic classes of stable vector bundles. Then I can define what I call, or what you can call graph kappa classes. So these are characteristic classes of bundles of this type, where I use this sort of generalized integration along the fiber to define so I do this, and this gives me homology classes in the base of the bundle. And the remark is that these classes generalized these well-known Miller-Meter-Mumford classes. So when you specialize to ordinary fiber integration, that's exactly how Miller-Meter-Mumford classes are defined. So the kappa of this epsilon L, you remember this generator in 0th dimensional graph homology. If I apply that to a sequence of, sorry, there's something, I'm sorry. I made a mistake here, sorry. I haven't told you what these, I have these characteristic classes of vector bundles, and I apply them to the fiber-wise tangent bundle, excuse me. So. Yes, so these, sorry, so if you have a sequence like this, this recovers the classical Miller-Meter-Mumford classes that you see in characteristic classes of smooth fiber bundles. And let me just sketch what I try. I mean, this will be very sort of brief and maybe mysterious if you haven't thought about these things before. But I want to convey the sort of general idea, hopefully. So if we study this particular manifold, G-fold connected sum of SD cross SD, and then we remove the interior of an embedded disk here to get a manifold with boundary of sphere, and here D should be greater than or equal to 3. And then roughly speaking, so here's these Miller-Meter-Mumford classes are featured in the computation of the stable cohomology of the diffeomorphisms of these manifolds due to Sarangalacius and Oscar Randall Williams. So let me draw you a cartoon picture. So I will be making some, telling a slight lie here, but to convey the idea. These kappa classes associate to the universal fiber bundle over BDiff of this manifold here. They, in the stable, when you let G go to infinity, so there's a range of cohomological degrees that are small compared to the genus, where this is an isomorphism. So this is due to Galatius and Randall Williams. Now, then you can look at, what we can look at is an enlargement of the diffeomorphism group, which is the so-called block diffeomorphism group, which classifies these so-called block bundles, which are more general than ordinary smooth fiber bundles. And there's a canonical map like so, and we can factor this isomorphism as follows. We can include these. So we observe that these can be viewed as graph kappa classes coming from 0-dimensional graph homology. So these include into a bigger polynomial ring generated by, well, for certain C that I will not spell out exactly what they are, but here we take all non-trivial graph classes. And roughly speaking, the theorem a theorem that I proved with Eve Madsen a couple of years ago is that you can compute the stable cohomology of this block diffeomorphism group in terms of these graph classes. So this is. So what I want to point out here is that, okay, so it's kind of funny because here we don't see any graph kappa classes, but here they all survive. So the question is what happens when with this map? So we have this graph kappa class here for some gamma of positive degree, and where does it map to? I mean, they don't seem to be necessary to account for all of the cohomology here. So it could be that they just map to 0. So this is, spawns some questions. So now I'll end just posing these questions. So now for a general smooth bundle, could it be that these are always 0? So is this generalized integration along the fiber always 0? When you take positive degree graph classes. And if so, a possible reason for them being 0 could be that they admit these kind of multiplicative structures in the resolution. So if so, does this, the forms on E admit an associative Poincaré duality resolution over the forms on the base for smooth bundles. So this is very speculative, but I mean these computations, which are basically these computations indicate that these graph kappa classes, something severe happens to them when you pass from to the smooth case. It could be that they're 0. We don't know that this is the case, but that's maybe the natural guess. So these are also some open questions that I think would be very interesting to answer. Okay, thank you.